Start talking
Is it
already.
started?
Just talk.
Okay.
It's running.
All right.
You ready to go?
Stop. Chapter
Okay.
6.
I know when to stop.
Chapter 6.
When I'm told to shut up, I know when to shut up.
Chapter 6, Thermodynamics. The study of energy and its interconversions. So we have thermodynamics, the study of energy and its interconversions in every daily life. Cars. Constantly, how we pump, it's how the engine goes. Alright, we got a few important terms we need to go over that will be used throughout the entire thing to understand concepts and to work out problems. Energy. The capacity to do work or to produce heat. We'll learn more about that later and its actual application. The law of conservation of energy. That energy can be converted from one form to another, but neither created nor destroyed. Potential energy and kinetic energy, which we will be trying to explain here. Energy due to position or composition. And then kinetic energy, energy due to the motion of the object. Alright. Heat. The transfer of energy between two objects due to temperature differences. Now, note now, this is not a substance or an object. This is just the feeling of the interconversions in daily life. Alright? So, heat and work, so we've worked, a force acting over a distance. Alright? State function / property function. They're the same thing. If you see them on a test, on a multiple choice or something, they mean the exact same thing. So listen. Refers to a property of the system that depends only on the characteristics of the present state. Now, we're going to go in depth on this because personally I struggled with it. So I get it now, but it took a few minutes, so we're going to get it. And then system and surrounding. These two are together, so remember them together. The part of the universe on which we wish to focus attention, system. Surroundings, the rest of the universe. Not a hard concept, give it a minute. Alright, so first we're going to explain potential and kinetic energy. So with this first, so this is a little chart. Now this is what's happening first, and then after something happens, this is what number 2 is. So number 1, we have, we'll use a different color. Green, red, blue, green. So we have ball A right there, and we have ball B down there. So potential energy, as we read, is energy due to the position or composition. So in this, now, let me just say, A and B, at their current spots and positions, both have kinetic and potential energy. But in this position, A has an increased potential energy compared to B. So this is where it's at. So after, the ball is never going to stay there normally, it's going to roll down the hill. So A is now going to be here, and B is going to get pushed up here. So now we're going to focus a little bit on the law of conservation of energy. That energy can be converted from one form to another. So when A rolls down the hill, it's going to lose potential energy. Now, it's not saying it's just transferring, flowing off, and just disappearing. We still need it because the law of conservation of energy. So it's somewhere. Where is it going? As A rolls down the hill, it's going to hit B. Now, as those two collide, now this is a good example as well of work. So work and energy, work and heat are both examples of energy. So in this is work. A will roll down the hill, hit B. Now, as B moves and shifts away into a higher position, the potential energy of B will increase. Now, when A gets to the bottom and rests in this little crevice in the bottom, the potential energy of A will decrease. So, potential energy is the energy due to the position or composition. So, in this position, A has a lot of capability to roll down the hill and hit B and transfer that energy. And then when it hits and they shift, B will get this potential energy, and then A, its kinetic energy will increase. Alright. Yeah. So after that, now we're going to go over heat and work a little bit. So I told you about, I already said the heat thing, never mind. Work. Yeah, I told you this is a good example of work, a type of energy, rolling down the hill and hitting something. And then, so I told you that heat is work and energy. Alright, so now we're going to go over state function or state property. You can see either of the tests are interchangeable, they mean the same thing. So again, it refers to a property of the system that depends only on the characteristics of the present state. So that's a little complicated. I didn't get it, I said it earlier. So let's look at the formation of NaCl solid. So you're given first Na plus gas. So Na plus, and then it's a gas, and then it's plus chlorine minus, these are the ions of it, and both sides start at that. Well, on the left side, it just shows its full, just from this state to that state. It is an exothermic reaction, meaning that it releases energy, and it's 411 kilojoules per moles. Alright, so that's the left side, it all goes through. So on the right side, these are the individual steps that it all goes through. Each little thing. Plus 107, plus 122, plus 496, minus 349, and minus 787. Now, when you add those all up and you put them all together, you still get negative 411. So, what this right here represents is a state function or property. So, you don't have to worry about all this stuff in the middle, you can just say, that's that. So, if that doesn't clear enough, then I've got a little something that will also explain it. A little analogy. Alright. So, analogy. The main point to remember when trying to identify a state function is to determine whether the path taken to reach the function affects the value. Alright? The analogy below illustrates how to tell whether a certain property is state function. Alright. So, every morning, millions of people must decide how to reach their offices. Some opt for taking the stairs, whereas others take the elevator in the situation. So the change in y, or change in vertical position, is the same whether a person takes the stairs or the elevator. Makes sense. The distance from the office lobby to the office stays the same, respective of the path taken to get to your office. As a result, the change in y is a state function because its value is independent of the path taken to establish its value. So this is the part where it really kind of falls together. In the same situation, time, or change in t, is not a state function. If someone takes the longer way of getting to the office, climbing the stairs, the change in t would be greater, whereas the change in t would be smaller if the elevator is taken, alright? In this analogy, change in t is not a state function because its value is dependent on the path. So, if that makes more sense, good. I'm glad. Alright. So now we're going to go over system, our final two terms, system and surroundings. So, this box over here is useful. So, as we read in here, the system, the part of the universe on which we wish to focus on. So, those two boxes, the inside boxes are both going to represent system, and I'm going to show you more about them in a second. So this is a system, and this is a system. So we're going to focus on those two when you're doing your experiments and your formulas and your equations. So the outside box is, as we said, the surroundings, the rest of the universe. So alright. rest of the universe. So, system and surrounding are pretty easy. There you go. Your equation that is occurring is your system. In chemistry, most oftentimes your system is literally just going to be your combustion problem and all that stuff. So, speaking of combustion problem, when you're doing a combustion problem, what happens? You cause heat, fire, yeah. So energy is E. We're gonna represent energy as E because yeah. So the change in E in a system. In the system, if the change, that's not E. If the change in E in the system is greater than 0, then it's going to be an endothermic equation. Now, you can see clearly it's an endothermic equation by the change of E is greater than 0. Now, another way you can do it is if you could show the pathway of energy. The pathway of energy is going in. Endo, you're absorbing the energy. The system, the thing that you're working on, the equation, has to absorb energy to occur. So that's the change of E is greater than 0 is endothermic. So now we have exothermic. The change of E is less than 0. Now, exothermic means that you're releasing energy, and then endothermic is you're absorbing energy. So which way are we going to draw the arrow? Yeah, you're going to draw it out, releasing energy. So you have endothermic and exothermic. And those occur in your surrounding, in your system, right? So now we're going to write a little equation that has to do with our energy. So we have E, like we were saying, change of E. The change of E is equal to, Q plus W. Now I said earlier that energy can be transferred by two methods. Heat or work. This was an example of work. Now, this is a clear example of, in a combustion equation, of energy moving via heat. So, change of E, the internal energy, so in here is the internal energy in the system, internal energy. The change of E equals Q plus W. Now, W in this is work, and the Q represents heat. So it's a pretty straightforward equation. If you are given a Q of 7 and a W of 5, your change in internal energy is going to be your Q plus W, your 7 plus 5, which is 12. And that's how you would use that's how you would find your internal energy. Alright, so now we're going to move to the topic of enthalpy. So enthalpy is equivalent to the total heat content of a system. Now, with enthalpy, we learned earlier that no, we didn't learn earlier. We're learning now. The change of H, delta H, is equal to Q. That's something you learn and you can know. So if a problem asks you find the Q, find the delta H, same thing. You can use the same formulas, get to the same spot. All right. So from here, we have a practice problem about, now this doesn't use a formula, this is just getting from one spot of what you're given to the next spot of what you need to get. So this is a practice problem. When 1 mole of methane, CH4, is burned at a constant pressure, 890 kilojoules per mole of energy is released as heat. Calculate the change of H, the change of energy, delta H, for a process in which a 5.8 gram sample of CH4 is burned at constant pressure. Okay, so one quick thing again before we do the problem is we learned this. I told you what exothermic and endothermic. So you can identify an exothermic or an endothermic with change of H, change of heat. Now internal energy, kind of the same thing as well, but they're used in different applications. So the change of H, if negative, equals exothermic. And then the change of H, when positive, is endothermic. So just keep that in mind in all your problems. So, because it can say in this problem, even in this problem, so when 1 mole of methane is burned at constant pressure of is released. Keyword here is released. So I said in this earlier problem, in the earlier explanation, the system and the surrounding, that when it's exo, it goes out of the system and goes in the surrounding. So with that, it releases energy out into the surrounding. So release energy. So this actually here, I'm going to need to know this, be able to read this and apply this to my problem, because this actually here is negative 890. Now it's written 890, but because it says of energy is released, so you need to know that step. All right, but this isn't here. We weren't given this. All right, so first thing we have to do always, and it's very helpful for many of these problems, write what you know, what you're given. So our Q, or change of H, is negative 890 kilojoules per mole. Now, we're given as well that the grams of CH4 are equal to 5.8. So CH4 is equal to 5.8 grams. So that's your mass, and you need to find. So this is, you're given your mass and you're given your energy of the problem. So what you're going to need to do is a little bit of stoichiometry. So I'm going to start doing the problem. So you're given 5.8 grams of CH4. All right. Now, in order to find the energy of your CH4, you need to multiply this times that. But it's in grams, and you're going to get extra, your units aren't going to match up in what you need and what your actual energy is. So you need to convert your 5.8 grams of CH4 to moles. The way to do that is go to your periodic table and find what's the molar mass of C and what's the molar mass of H. Now with H you're going to multiply it times 4. Now, so C plus H all adds up to be 16.04 grams. Now, molar mass, so it's grams, so it's moles over grams. So when you're doing it, CH4 and then CH4, make sure you write these out so you can cancel them. So 5.8 grams of CH4 cancels with grams of CH4. So when you're all done with that, you're left with 0.36 moles of CH4. Alright, so now you have moles and you can keep working the problem. So now, you're going to start with your 0.36 moles of CH4, and you're going to multiply it times negative 890 kilojoules, goes on the top, per mole of CH4. Now, there's just one mole on the bottom, so you don't have to write it. So when you multiply that together, you get your number, and that is negative 320 kilojoules, because your moles of CH4 and your moles of CH4 cancel out, and you get negative 320 kilojoules. Right? So we're on the next section now. We're going to be talking and working with problems for calorimetry. So, calorimetry, the science of measuring heat, is based on observing the temperature change from a body when a body absorbs or discharges energy as heat. It's a little complicated, but we'll get into that. Specific heat capacity. So specific heat capacity and molar heat capacity are kind of one and the same. They are different ways of representing a number via how to get from one spot to another with grams or moles. So specific heat capacity deals with grams, and specific heat capacity and molar heat capacity deals with moles. Alright, so specific heat capacity, the energy required to raise the temperature of 1 gram of a substance by 1 Celsius. So if you have 1 bit of water, however amount of heat it takes for that water to raise in 1 degree Celsius is its specific heat. And it's the same for amount of moles of something. The amount in that'll change. Now you can have your molar heat capacity, but we more often use our specific heat capacity. So specific heat capacity is written as joules. Your units for this are joules. Usually going to use Kelvin, or you could use Celsius. So it could be joules over Kelvin times grams, or it could be joules over Celsius times grams. And then for your molar heat capacity, it's the same, but a little bit different. It's joules over Kelvin times moles, and then, or it could be joules over Celsius times moles. Alright, so now that we've gotten that down, the specific heat of something changes as you increase the amount. So if you have 1 gram of water and it takes a certain amount to go up in 1 degree Celsius, then now if you have 2 grams of water, it's going to be twice as much to go up that same one. So it's based around the amount of substance. Alright, so you can define specific heat capacity as such, and you can also list it out. You can list it out like this, and then you can define this. So specific heat is often represented as a C. So C equals your energy, joules, times your mass, your grams, times your change in temperature. Now, this is an equation that you're given for specific heat capacity, but we often, for this example problem, we're going to change it up a little bit and switch which way we're applying this formula for what direction that we need to work with, what we're given, what we're not given. So we're going to switch it up a little bit, and now the Q is divided by grams times change of T. So we're going to, and we represent the grams as the mass, so we can just put M, but no, it's not mass. You have to know it's mass, not molarity or moles. Alright, so you're going to multiply it over and you're going to get Q equals M, specific heat, and delta change. So one way to easily remember this is Q equals M cap. Looks like an A, it's a change, it's the delta sign. So you can remember this with Q equals M cap. Pretty simple. Alright, so from there, on tests and on multiple choice problems, when they ask you to find certain things, you're going to need to know, for like this, for your specific heat capacity and with your calorimetry problems, you're going to need to know your specific heat for a lot. Sometimes you'll be trying to solve it and you'll have your energy, your mass, and your change in temperature, but often or not, you're going to have to find something else in there, your energy in this problem, so you're going to need to know your specific heat. It's not something that you can just go grab or something that is given to you for water. Water, you are supposed to know, and you're responsible to know, that water, the specific heat of water is 4.18 joules over Celsius times grams. And there's plenty of others, and when they change states of matter, they change. So if you see a H2O gas, it's going to be different. You need to know that. It's going to be 2 point something. But often, more than not, they'll give you that, because you can't figure that out somehow. Alright, so we're going to do the problem now. So, like I said in the other example problem, write what you're given. So, we have 50 milliliters. So let's read the problem. Suppose we mix 50 milliliters of a 1.0 molarity HCl solution at 25 degrees Celsius with 50 milliliter of 1.0 molarity NaOH also at 25 degrees Celsius in a calorimeter. After reactants are mixed by stirring, the temperature is observed to increase to 31.9 degrees Celsius. The density of the solution is 1.0 grams over moles. Alright, so what were we given? So we're trying to find the solution. So you can automatically assume that the volume of the solution is going to be 100 milliliters, because you're given 50 milliliters of HCl and 50 milliliters of NaOH. So we're given 100 milliliters, which is your volume, and then you're given, so the temperature is at 25, and then it changes to 31.9. So you're going to do 31.9 minus 25.0, because in our equation that we're working on, we're looking for the change of temperature. So it was 25, they're both 25, and then when you put them together, it raised to 31.9. So you're going to need to find the change in that, which is, I believe, 6.9 degrees Celsius. Make sure you have your units. So we have our change in temperature. So we're trying to find Q here, because it's asking, after reactants are mixed by stirring, the temperature is observed to increase. Yeah. So we're trying to find the Q. So we have the change in T. We're given our specific heat in the problem, and then we need to find the mass as well. So we're given the density. The density of the solution the solution is 1.0 grams over milliliters. So we have our milliliters of the full solution, and we have our density. Something we can do, which is very beneficial, is take our grams over moles, multiply it, or take our density, multiply it by what you know it's going to be, 100 milliliters, grams over milliliters, make sure that's correct, and then multiply that times that, and you're going to get 1.0 times 10 to the second grams. Yes. Now, that's our mass. So we have our mass, we have our change in temperature, and we have our specific heat. So in order to find Q, what does the equation formula say to do? Multiply it all out. So make sure you write all the units, because if you got your units messed up, there's probably something wrong with your calculations and something's going on. So you got 4.18 4.18 joules degrees Celsius over degrees Celsius times grams times your 1.0 times 10 to the second grams over, grams, and then times as well your change in temp, 6.9 degrees Celsius. So your Celsius cancels with your Celsius, your grams cancels with your grams, and then when you multiply that all together, you get 2.9 times 10 to the third joules. And now you have found the heat. You have found the heat, which we learned earlier. The change in heat is equal to Q. You found your heat of the solution. Thank you. So this is Hess's law and the applications in enthalpy. So first, we know that enthalpy is a state function. We learned earlier a state function is something that you can go from this to that state, and all the little steps and pieces in the middle are not applicable. You can just take the number and go to that step. So we know this, you're supposed to know this. Enthalpy is a state function. Alright. So because enthalpy is a state function, we're going to work on Hess's law now based off this. This means that in going from a particular set of reactants to a particular set of products, the change in enthalpy, the state function, is the same whether the reaction takes place in one step or in a series of steps. So we're going to work on a practice problem. But first, we need to know a few concepts and kind of workarounds that make it easy, and we've found out that work for finding the delta H for certain problems. So characteristics of delta H for a reaction. 1. If a reaction is reversed, the sign of the delta H is also. So that would mean if we were to flip this around, this first C plus H2 yields CH4. If we were to flip that around, it wouldn't be exothermic anymore, a negative delta H. It would be endothermic. So it would be just 74.80 kilojoules. It wouldn't be it would be a positive, it would not be a negative anymore. Alright. So now the second one is a little more complicated. So the second, the magnitude of the delta H is directly proportional to the quantities of the reactants and the products in a reaction. If the coefficients in a balanced reaction are multiplied by an integer, the delta H also needs to be multiplied by that same integer. So that just be, if I needed to multiply this equation by 2, this whole equation by 2, to cancel something out or whatever, that would mean this number right here, I would need to multiply that by 2. You wouldn't change the negative, you wouldn't do anything like that. You just multiply that by 2. But we are not multiplying this by 2 yet. Alright. So let's work on the problem now. So the problem says calculate the delta H for combustion of CH4. And we are given this. So when you're given this and you need to calculate the combustion of CH4 using your enthalpy is a state of function, you need to have an equation that you want to get. You want to be able to manipulate these to get what you want. What do we want? The combustion of CH4. Combustion we learned very early on. So CH4 plus O2 yields H2O and carbon dioxide. So there's nothing wrong with this. It's not balanced. You gotta balance it. We got one C here, we got one C. Alright, 4 C's. 4 H's here. You only have 2 H's on this side. So you're gonna put a 2 here. And then you look out your O's and you're gonna need to put a 2 here as well. So now you got 1 C on either side, 4 H's on either side, and 4 O's on either side. So you have a balanced chemical equation now. Alright, so this is what we want to calculate the delta H for combustion of CH4. So this is your combustion of CH4. Now, these are the components, the steps that we don't look at in the enthalpy in a state of function. You just look at this. Well, we don't know what the delta H for this reaction is. We're trying to find it. So these are the little steps in between, but we know it's going to equal the right thing because the state function. So we have to cancel out and we have to move around pieces to make this equation. So right now, the first one you can tell easily, you want your CH4 to be on your reactant side. So you're going to want to switch that around. So what I do when I work these out, I flip the problem and I rewrite my delta H on the same column. So I know what I'm doing and when I'm shifting and all that stuff. So you want to mimic this. You want to mimic this one. So let's make that. So you got your C, H4 yields C plus H2. And now your delta H, like I said earlier, if a reaction is reversed, the sign of the delta H is also. So now this is not negative 74.80 kilojoules. It's 74.80 kilojoules. Alright, so we're continuing, and the second one, you see the only thing in this equation that's in this one is your carbon dioxide, and it's on the right side. So you can just put that bad boy right down under. Carbon plus O2 yields carbon dioxide, and then we've done nothing to change the equation. It looks right, it fits in this, matches in this, so we're not going to change our delta H. So it's still negative 393.50 kilojoules. Alright, so now next we have our H2O that we need to find through this one, and it's again on the right side. It's still in the product side, so we have to just put it right down. All right. All right. So welcome back. Sorry. When I was solving the problem, I could tell something wasn't lining up, and it's because I had written my equation wrong with the practice problem. So this is C plus 2H2O yields CH4, not C plus H2 yields CH4. So this CH4 was on the wrong side, so we flipped it to the reactant side, and we flipped our sign like we learned here. So now we did the other one, and then we have this. So something's wrong here. So you work down. You can get rid of stuff periodically. So if something's on a product side and on a reactant side to the other one, you can cancel them out. So we have a C, we have a carbon on the product side here, and then we have carbon on the reactant side here. We can cancel them out, and they won't occur in the equation that we need to get. So if those cancel out, we're still left with everything else. But if you notice, now they work down. So if they're both in the same product and both in the same reactant side, they will just add or subtract whatever they're needed. When you get your O2 and your 1/2 O2, you get 3. You get 1 and 1/2 O2. Well, you have 2 O2 in your final. So what are you going to need to do? You're going to have to multiply this entire one times 2. That's going to put a 2 here, a 2 up here, which cancels out and becomes a 1. and then a 2 over here. Now, don't forget this, because this is the most important step. When you multiply everything, all your stuff, coefficients, all of that, your proportions, you're going to need to multiply this by 2. And that is going to be, let's pull out a calculator. That's going to need to be 285.50 times 2 is negative, now you're going to leave the sign, negative 571 point, nope, it's just negative 571 kilojoules. Alright, so now if you realize, if you put all this together, your 2H2O here cancels out with your 2H2O on the other side. So what you're left with in the end is CH4 plus 2 O2, because you have an O2 here, and you have 1 O2 here, because you multiplied the coefficients, yields 2 H2O, again, you multiplied your coefficients, so you have it all set up there, plus your carbon dioxide, which is left. And then you get your problem. Well, refer back to your problem, what is it asking for? Calculate the beta H, the delta H, for the combustion of CH4. What are we going to need to do? Now that we've changed all these delta H's for each equation, we have to add them all up and figure out what our delta H is for this formula. And when you do it, and you put it all together, you should get negative 890.30 kilojoules. And that's how you apply enthalpy to Hess's law. Alright, we're going to work with the standard enthalpy of formation, and we're also going to work with comparing enthalpies of combustion. Alright, first we're going to work with the standard enthalpy of formation. So the standard enthalpy of formation is the change of temperature of F, the bonds, the change in enthalpy that accompanies the formation of 1 mole of a compound from its elements with all substances in their standard states. Alright, that's a little complicated, but this next one also helps it. So the standard state for a substance is a precisely defined reference state. So the standard state of a substance is basically when it's all in a certain condition limits, it will be easier to work with in problems, and that's what we like, right? So the conditions, the standard enthalpy conditions is 1 atm, 1 molarity, and 25 degrees Celsius. If it hits all of those, then it is in standard state, and it's easy to work with, and it has less variables to mess up and screw your equation. Alright, so we also need to know for working with the standard enthalpy that we need to know a past formula that we looked at briefly, didn't explain much, that we're not going to use. So the change of H, the delta H, equals now this is a little this is the very convoluted version. They might show you this and ask for this, and it might throw you off, not know what it is, but this actually just turns into products minus reactants. Change of energy in products minus reactions, both also being energy values. So here we're given a problem equation, and we were given in the problem the energy of iron oxide and aluminum oxide, and from there we're supposed to figure out products minus reactants to find the delta H. Well, we weren't given what 2 aluminum is and 2 iron is. Well, that's alright. When something is in its standard state, there's only one of it, right? It's not mixed in with other ions. Now the coefficient in the standard state, don't worry about it, because it's just trying to match, so there's one of it. So we can assume, because it's in its standard state, that it has zero effect on the change, on the energy, and this has zero effect on the energy. So that would mean that these two compounds are the only two compounds that actually assist, or I guess impact the change of the H. So what is our formula? Delta H equals products minus reactants. This is the reactant side, this is the product side. So we're going to do products minus reactants. We're going to do negative 167.6 minus our negative 826 kJ. And when you put those together, your products minus reactants, you are going to get, let me calculate that up.
That's 8.
Is it? You're going to get negative 850 kilojoules. And it's simple as that.